Do you ever wish that you were on a spaceship zooming through the universe? Well, we all are. We are on spaceship Earth, and we are going pretty damn fast. Today, we're going to explore just how fast this vessel that we are exploring the cosmos on, just how fast is this thing going? Now, the first factor to consider for our movement that we're experiencing through the cosmos is the rotation of Earth. What's responsible for day and night? And of course, the speed that you would experience from this rotation, it varies depending on where you are. If you're right up at the North Pole at the axis of rotation, you are only spinning around once. You're staying in the same spot, just spinning around once. 0 meters per second. Whereas if you are at the bulge of the equator, where you're going to experience the fastest speeds of rotation, you're going to be traveling at 460 meters per second. Now, this sounds fast, right? 460 meters per second is equivalent to 1,670 kilometers an hour. But mate, these are sloth speeds in the universe. This is slow. There are much faster speeds than this that we need to consider. So let's look at a little bit of a bigger picture here. So next, we need to consider our movement around the sun, who we have been in a very committed 4.5 billion year long-term relationship with. All of that long distance, mind you. Now, why did I just make the sun white? Well, you'll have to tune into another video for that. But the sun ain't yellow, it just looks that way from Earth. If you're looking at it from space, it is white. So I'm making my sun white. We do things right here. We are moving around the sun, one orbit, complete orbit, every year. The speed that we are traveling, 30 kilometers a second in that orbit. And that is the equivalent of one Earth diameter every 7 minutes. So every 7 minutes, we are completely transposing ourselves one Earth diameter through space. Over the period of a day, we move 200 Earth diameters. And this is what moving 200 Earth diameters would look like, scaled down to 10 seconds. As you can see, not a trivial distance, and a distance that has surprising effects on things. So the fun part of this is that after moving these 200 Earth diameters, you've moved so far, 2.6 million kilometers around the orbit, that the part that the previous day was pointing directly towards the sun will no longer, after one full 360-degree rotation, be pointing towards the sun anymore. So because of this vast distance we're moving, every day there's two different types of days. The sidereal day, which is one full rotation, 23 hours and 56 minutes, and then the solar day, which takes a little bit longer for the sun to get back into the same position, takes an extra 4 minutes or 361 degrees of rotation for a total day of 24 hours, which is what we're more familiar with. Now, the cool thing about this, the reason why these numbers, 360 degrees in a circle and 365 days in a year, the reason why they're so similar is because the first known calendar was made by the ancient Sumerians, who had a 360-day calendar, which consisted of 12 lunar cycles. So pretty much the 12 lunar cycles would equal 354 days, and they just rounded it up to 360 because they had a base 60 number system. So that's why the number of degrees in a circle is so similar to the number of days in a year. A very cool fun fact. Thanks, ancient Sumerians. So we have an understanding of how we're moving around the sun, but to understand how we're moving throughout the whole universe, we need to take into account our galactic orbit. And to do one galactic orbit, which would equal one galactic year, that takes 230 million years. Coincidentally, not only is one galactic year 230 million years, we are also traveling at 230 kilometers a second as we go in this orbit around the galactic center. And we also bob up and down a little bit through this orbit. We'll go above the galactic plane and below. And that's all part of that 230 kilometer a second motion. To give you an idea of how many galactic years we've had, our sun, it's only 20 years old on the galactic year timescale. We've only done 20 orbits of our galaxy. The next part of this puzzle involves comparing our movement to other nearby galaxies, which all seem to be moving towards this one central point we call the Great Attractor. We're in the Laniakea supercluster, and we are all heading towards this point. But do we measure our speed relative to the other galaxies? Or do we find some type of universal standard? What we use is the most universal standard of all. These are heading towards the Great Attractor, and we use the CMB, the Cosmic Microwave Background Radiation. That is how we tell how fast we are moving towards the Great Attractor. Now, what is the Great Attractor? It's just a central point of gravitational attraction between our supercluster. The main reason why we don't really know what the Great Attractor is yet is because it's in line with our galactic plane and the dust from our galaxy is really blocking our view. But it has a massive, massive trillions of solar masses, so there's something hiding there. We just don't know what it is. In order to understand how fast we're moving with respect to the cosmic microwave background radiation, we need to look at some pure, raw, unedited versions of this image. Now, I'm sure that a lot of you would have seen this glammed up form of the CMB. This is after a whole lot of processing. Right up here, this is what it's all about. This is the beautiful, raw, unaltered CMB. And the reason why? The fluctuations are there. They're just incredibly tiny, and the pixels on your screen probably can't even fluctuate that much. Or if they can, we can't tell the difference. Because the average background temperature is extremely uniform. We are measuring tiny little fluctuations with the CMB. So this average temperature is pretty much standard across the whole of the CMB. We are getting variations of only 1 part in 100,000. In order to be able to detect these slight fluctuations of only 1 part in 100,000, we need to increase the contrast, enhance the contrast of the image just like you would with a really dark photograph that you're editing so that you can see the small features. Now, the features that are revealed, of course, in the middle we see the Milky Way, but we also see this darker patch over here, which is representing a colder CMB that we are detecting. And over here we've got this lighter patch, which means we're detecting the CMB to be slightly warmer in this direction. We're receiving more radiation because we're moving in this direction, therefore colliding with more of the CMB as we move in this direction. And this is showing us the most accurate representation of Earth's relative velocity through space, which is 369 kilometers per second. Now we can forget about pretty much everything else that we've seen because this is the most perfect standard to measure our variation. So this is taking into account everything. The movement of the Earth around the Sun, the movement of us around the galaxy, and the movement of the galaxy itself. This is the overall gold standard for how fast we're moving. Just to give a quick mention of what happens with these further images, which aren't required for analyzing our speed, we then remove the temperature dipole and further increase the contrast to reveal all of the minor temperature fluctuations. And then, of course, we're left with this big, ugly Milky Way disturbance in the middle. That's subtracted using complicated techniques, and this is the final nice CMB that you're used to. But it's a really beautiful version of it, this one up here. It gives a lot of amazing information that you can't get from this CMB image. So yeah, it's a pretty great image. So although we have an answer for how fast the Earth is moving relative to the CMB, we didn't quite answer how fast is the galaxy, the Milky Way galaxy, moving towards the Great Attractor when referenced to the CMB. And to do this, we need to figure out which direction this movement is compared to this movement of the sun around the galaxy. And it turns out that the galaxy itself is actually going in this direction. So it's traveling in that direction at a speed of 600 kilometers per second. And the reason why Earth is appearing to be going at 369 kilometers per second is, of course, because we're traveling in the opposite direction of the movement of the Milky Way galaxy. Now, that means we are going to be going even faster in another 100 million years when we're on this side of the galaxy, and our galactic speed is going to be stacking onto the speed of the galaxy approaching the CMB. We'll be going at close to 800 kilometers a second then, which will be our top speed. So now that we've calculated all of these cosmic speeds, why not represent them in Earth diameters traveled per day? Just like we did with the movement of the Earth through the solar system, traveling 200 Earth diameters in a day. Well, it turns out that the solar system moves through the Milky Way at a rate of 1,533 Earth diameters a day. The movement of the Milky Way galaxy through the cosmic microwave background radiation is 4,000 Earth diameters a day. And all of this altogether results in a net movement of the Earth through the cosmic microwave background radiation of 2,460 Earth diameters per day. Wow. Now, I wanted to come up with my own fun system for comparing these cosmic velocities. And it turns out that they all scale pretty well. If you scale them down by a factor of 7,000, they equal some velocities of animals on Earth. So, scaled to this, Earth's rotation would be equivalent to a sloth. Our orbit of the sun would be equivalent to a squirrel at full sprint. Our sun orbiting the Milky Way would be equivalent to a cheetah at full sprint. And the Milky Way relative to the CMB would be equivalent to a peregrine falcon in a dive. So next time you're feeling lazy, just remember, you're constantly moving. You're on an epic voyage through the cosmos, whether you like it or not. This movement's happening, and we are just all along for the ride. So I had a lot of fun putting this one together. I couldn't help myself. I had to make two more. These two extra ones are like infographic style videos that show visual representations of these cosmic velocities in terms of Earth diameters with actual little Earths moving across the screens at relative rates. So check that out. If you like this video, you'll like those.